So for spherical coordinates, we start with the main idea that rho is going to be our radius, but this time it's going to be the radius referring to the origin. So it's actually the distance to the origin. And so, of course, quite often we will end up seeing x squared plus y squared plus z squared being translated as rho squared. So now the way this works is we start with the sort of the orientation of the North Pole. So looking at, imagine I'm going to draw a planet here or something like that. If there was a sphere centered at the origin, then the North Pole would be up here, right, for the planet. So what we're going to do is we're going to go up the vertical axis to rho. Sorry, I should have explained. So I'm looking for the point with coordinates rho and phi and theta. I guess in the book it draws phi a little bit more like this, but it's the same character. So let's see. So I go up the vertical axis to phi, and then if you look in this vertical plane right here, so this is the one in the xz plane, we're going to rotate now down in that plane by some angle phi. And so now we have some point which is, say, I'll draw it in blue now. It's like right here, and it's suspended above this point on the positive x-axis. Then what we will do is we will rotate that point around by some amount. So let's call this theta. So we're going to come around out here to this point. Actually, I guess maybe I should stick with it and call it dots. Okay, to this point right here. And so this is our point, rho phi theta. Okay, so once again, just to review, you go up toward the North Pole by distance rho, and then you swing down over the positive x-axis, and then you rotate that whole thing counterclockwise in the xy plane until you get to the point that you're interested in. That's how we describe the point with coordinates rho, phi, and theta. And so the formulas for this coordinate transformation is that our x-coordinate is given by rho sine phi cosine theta, and y is equal to rho sine phi sine theta, and then z is given by rho cosine phi. Okay, and so now if you look at this is sometimes a helpful conversion if you're going back and forth between cylindrical and spherical, is that if you take these two, if you look at x squared plus y squared, then you end up with rho squared sine squared phi cosine squared theta plus sine squared theta after you factor out the common rho squared sine phi. So this part here cancels to 1 by the Pythagorean identity, and what we're left with is r squared equals rho squared sine squared phi, or r equals rho sine phi. And so let me just take that one and kind of swing it over here by this one for contrast. So this is kind of how you understand what cylindrical look like, or the relationship between cylindrical and spherical. So it's not actually hard to see where the z coordinate is by looking at the figure right here. If we look at this triangle in the green plane, you can see that the cosine of phi is going to be the adjacent side over the hypotenuse. And from the arc, you can see that the hypotenuse has length rho. So that gives you that the height right here, your z, is going to be rho times cosine of phi.